So now we will start introducing a tiny bit more notation, just 3. I promised to discuss Bellman equations. So the first notation that I will introduce, as I already alluded, is called V star. This is the value of state. What does it mean? It tells you the value of the expected reward if you're starting at state S and act optimally. It's like, what is the best I can do when I'm starting in the state S? And as I alluded to you previously, maybe the state which is next to our reward would have higher value than the state which is very far away. So it's expected reward starting at S and acting optimally. So in this case, instead of saying acting optimally, I could have said acting according to the policy. That from that point on, you're doing the best you could. Now I am going to introduce you something which will sound a tiny bit counterintuitive, but we will see the value of it. So now I am going to introduce something which is called Q value, again star because it is an optimal one, which will be defined on state and action. Because here I don't actually care which action I take. I assume that somebody tells me what is the best set of actions. Here I'm decomposing it and stating that it will be an expected reward if I'm starting at state S, taking an action A, and then acting optimally or acting according to the policy. So expected reward starting at S, this is like before, then taking action A and acting optimally afterwards. And acting optimally until the end. Okay? We already seen our policy. I will just remind you and say that we also have our policy pi, which we shouldn't forget, correct? This will be our policy pi, which takes S and returns us the best action that we can take. Okay? So those are the 3 quantities. And what the Bellman equations do, they actually connect all these 3 quantities together. So let's start first by connecting the value of the state and the Q function, okay? And the Q function. So we can say that the value of state S is going to be, as we said before, the value of the state if we start at state S and act optimally. So towards this optimal behavior, we need to select the best possible action. So pretty much what we can say that it's going to be it's going to be max A QSA. So let me explain to you. So from this state you can take many possible action, but you say if I want to continue acting optimally, I need to select the best action, and to do so, which are the best action, I'm going to try different Qs with different possible A's and select the one which gives me the highest Q. Okay? Another way to write it, we could have just written it, it's going to be QS pi star S. So this just tells us, instead of explicitly showing that we're selecting the best possible action, this is the action that should be written in our policy. Our policy will tell us what is the best action to take. Okay, so this is the definition, this is the connection between V and Q. And what I will do next, I would recursively define the values, the value of V. So what we would say that when we are actually maybe, yeah, let's start with Q. Q would be easier to start. Let's start with Q. So in this case, we are in state A and we took an action A. I will start explaining to you as if we deterministically know where I will end up. Let's say my transition function tells me that whenever I'm in state A and I take action A, I'm always going to be at the same exact place. So in this case, what I know will going to happen. So whenever I took my step, first of all, I'm going to collect the reward. I am going to collect the reward, okay, plus I'm now in a new step and my value would be dependent on whatever I can collect from that state, correct? I am now end up being in some state S prime, and I want to see what will be my best expected reward when I'm going from that S prime up to the end. So here we are going to write V S prime. There is something missing here, and it had to do with the definition of discounted reward. You remember we said that we value the current reward more than the future reward. That's why whatever we are going to collect from the state S prime, we will weigh by the gamma, by the discounting. So again, we are taking our path from state S towards, our completion. We are dividing it. We are stepping one step to state S prime, collecting the reward and saying, and whatever you're going to collect is going to be determined by the value of state S prime weighted by gamma. Now, the only thing that we need to add is actually to think that in reality, whenever you're taking your action A from state S, you're not necessarily guaranteed to be in this particular S prime. There are many possible states where you can end up, and you need to average across all these possible states, again, depending on the probability to end up there. So we will now look at all possible states S prime where you can end up, and we will look at the likelihood of actually getting to this particular state. And our transition function would tell us what will be that likelihood. So again, there are two parts to it. One is we are taking into account how likely is to end up in some state S prime, and within it, we are collecting the immediate reward, plus we are looking at the value of the future state discounted. Okay, so here we just defined our, and let me add the stars here, our optimal stars. And now let me just define V in a similar fashion. So what I want to do is define V recursively, meaning to define V of this state in terms of V's of neighboring states. So here we are writing V of the state. And you remember that based on our formula, V is just max over all the A's of Q star SA. So what I can do, I can just take this expression, and instead of having here Q star, I would write what we already estimated. I'm just going to copy this whole expression. So we're going to have max A, and then instead of having Q star SA, I'm going to write this full expression. And let's see what we will get if we do that. So now we actually got here the full expression for V of state S in terms of other states where you can end up going after the state S of the neighboring states. So those equations are called Bellman equations. And let me just show that we finished the Bellman equations. And these equations will be key for us when we are defining an algorithm for computing our MDP policy.